How to master Maxwell's equations math. Imagine trying to understand how invisible forces work together to create the electromagnetic waves that power your phone, radio, and even your microwave. That's what Maxwell's equations explain. They are the foundation of how electric and magnetic fields interact. To truly master their math, you need to start with the basics of vector calculus. Focus on understanding divergence, curl, and gradient. Divergence tells you if a field is spreading out or coming together, curl shows how it rotates, and gradient helps you see how a field changes in space. These operators are like the language of fields. Next, get comfortable with partial derivatives, especially those with respect to time, because electromagnetic fields change over time and space. Now, look at each of the for Maxwell's equations one by one. First, Gauss's law for electricity links electric field divergence to electric charge density. It's written as divergence of electric field equals charge density divided by electric constant. This shows how charges create electric fields. Second, Gauss's law for magnetism states that divergence of magnetic field is zero, meaning magnetic monopoles do not exist. Magnetic field lines are continuous loops. Third, Faraday's law of induction explains how a changing magnetic field induces an electric field. It's written as curl of electric field equals negative rate of change of magnetic field. Lastly, the Ampère-Maxwell Law shows how magnetic fields are generated by electric currents and changing electric fields. Its curl of magnetic field equals permeability of free space times current density plus electric constant times the rate of change of electric field. To get good at these, practice converting equations between their integral and differential forms. Use vector calculus theorems like Stokes' theorem and the divergence theorem to switch between forms. This helps you see the physical meaning behind the math. Apply these equations to real-world problems like analyzing how signals travel through transmission lines, waveguides, or antennas. Practice solving boundary conditions and partial differential equations because fields often depend on the shape and materials involved. Use different coordinate systems like Cartesian, cylindrical, or spherical to match the problem geometry. This makes solving easier and more accurate. Keep practicing by working through problems involving electromagnetic waves in circuits, devices, or free space. Simulate fields with software to see how they behave in different situations. Remember, understanding Maxwell's equations is not just about memorizing formulas but about grasping how electric and magnetic fields interact and propagate. Building a solid foundation in vector calculus and differential equations is key. Focus on understanding each equation's physical meaning and how to manipulate them mathematically. Practice converting between forms and applying them to practical electrical engineering problems. Over time, solving Maxwell's equations will become more intuitive, and you'll see how they underpin many modern technologies like wireless communication and radar. Stay consistent, work through problems step by step, and you'll find yourself mastering the math behind the fields that shape our world.